Now, coming back for the second part, and it technically goes with what we were talking about in the last one. We want to make sure that we're keeping tabs on how we're going to calculate our standard potential for this overall process. Now, the formula that we're going to use is actually given to you right here. The standard cell potential is going to be equal to the potential for our cathode minus that of our anode. If we use this formula as it's given, we don't have to worry about flipping the sign, because if we put it in place in the correct order, we're going to end up with the subtraction happening normally, or if we actually have a negative value for our anode, then it's actually going to end up still giving us a positive value. So you want to make sure that you're keeping a little note of that. This is the formula that we're going to use, and it helps us so we don't have to worry about paying attention to the whole flip the sign part. Now, the easiest way that we're going to always look at this, we can figure out where the electrons are going based on figuring out which one is going to give us a positive standard cell potential. Okay? If we end up with, we subtract it and we get something negative, we know that that's not where it's going to happen. We know that that substance, that electrode, whatever it is that we're using, is not actually our cathode, and it needs to be flipped. Now, when we look at this cell potential, again, we're not looking at generating electricity just to say, ooh, we did it. We're looking at it to see how we can actually produce something from it. Now, work overall, we know is we can't get the maximum out of it. There's always going to be something that limits our ability to use that energy that's being produced. If we have a spontaneous process, part of that is going to be just as the electrons flow through the wire, depending on what type of wire it might be. So, when we want to figure this all out, we have another form that we're actually going to take it. To figure out the maximum cell potential, we're going to go back to what we call delta G. Now, as you see on the screen, it says that the maximum cell potential is directly related to the free energy difference between reactants and products. So, maximum cell potential, free energy. That free energy, again, just like we talked about before, is looking at that overall excess energy that we were dealing with. And we're going to look at this formula that sort of comes into place. Sometimes you'll hear this brought up and it'll say delta G naught. Okay. Now, if we're looking at it, the key to knowing which version of delta G that you're looking at, look at what information you're given in the question. Okay. So if you look up and they're giving you electrochemical information, they're giving you voltages and standard percentages, this is the delta G that you're going to use. You want to mark that on your reference sheet so as you practice. Now, we're also going to introduce what's called Faraday's constant. Faraday constant, which is 96,485 coulombs per mole of electrons. Many times you'll actually see this written instead of 96,485 is 96,500. Still the same number, it's just a rounded version. You'll still come out with the same information. I think in your reference sheet it actually gives you this version to work from, which is perfectly fine. Okay, now notice that in this formula the delta G that we're going to get has this negative value right up front. Again, if it's a spontaneous process, delta G is going to be negative. So if things are going as they should, spontaneous process equals negative delta G value. And I'm sorry for things seeming like they're going up. I'm trying to write on the tablet and handwriting is a little interesting. But we continue from there. Now, this means that if we're looking at our overall reaction, let me go back. I can actually determine how much free energy is going to remain based on these calculations. If I can figure out the standard cell potential, I have Faraday's constant, and I know the number of moles of electrons. Sorry, I didn't mention that. So looking at this N that we're looking at is it's not just for number of moles and actual number of moles. This is actually moles of electrons. Okay, so if I have the information for that, I can figure out what that difference in free energy is, and even how I'm going to be able to use that information and what I could possibly power through that type of energy being given off. Now, when I look at my cell, my galvanic cell sitting in front of me, notice before we're looking at things in a standard state. Standard state is always that perfect situation, okay? Sort of like when we looked at STP. You know, STP was 1 atmosphere, 0 degrees Celsius, made things behave in a certain way. Same thing for our standard conditions for our standard cell. But we know that we can also sort of change things up a little bit to give us a different result. What do I mean? Well, take a look at the diagram on the screen. Notice I have the electrodes are the exact same. I have in the containers, I have the exact same solution. The only difference is I have a higher molarity in my container on my right side. Now, this being the case, because it has a higher concentration, that means it's also going to reduce a little bit more. So, even though we have a lower concentration here, it's actually the electrons being pulled towards the higher concentration. Because of that fact, we have this silver ion or silver electrode as our cathode, whereas the other one, you can see that it's wilting away, deteriorating, is our anode. Okay? Now, when we want to determine what the actual relationship is between those cells at differing concentrations, we're going to use what's called Nernst equation. Nernst equation is derived from, it's actually a lot more math than you will ever need to know. But the biggest thing that it's actually showing us is how much would it change, how much would the cell potential change if we're not at standard conditions. So we look at it in two situations. The first situation is if we have a reaction that's not at equilibrium. I can tell that it's not at equilibrium because I see Q. So I'm going to put not EQ. Okay. Now, if it's not at equilibrium, that means that we're still going to use the information from our standard state, but we're going to subtract from it this value divided by the number of moles of electrons, and the log times the log of Q. Now, Q is what we call is based on what we call a law of mass action. It's looking at the concentrations that we have at that given point. Many times it's going to help us to learn which direction that equilibrium we have to go to equilibrium. But in this case, what we're going to do is we're just going to use the concentrations of our solutions. And you can usually look at the reaction to determine the overall balance equation to figure out what's going to be on top, what's going to be on the bottom. Either way, you're going to have products over reactants. And of course, these are the concentrations of it. So, now, again, Q means we're not at equilibrium. Q not at EQ. Easy way to think about it. Now, if the reaction actually is already at equilibrium, we're going to do the same exact thing, but notice here we don't have to subtract anything from there. Our standard cell potential is still going to be that value, which is actually a calculated value, divided by the number of moles of electrons times the log of K. K is what we call our equilibrium constant. EQ constant. Okay? And I just realized I spelled constant horribly wrong. Please forgive me. Now, equilibrium constant is the exact same thing as we looked at for Q, except we have reached the point of equilibrium. So, we're still going to do products over reactants, concentration products over reactants. And we're still going to place everything in there just as normal. Now, one of the things I want to be very clear of, equilibrium does not mean that we have the same amount on both sides. What we call equilibrium is when the forward rate is equal to the reverse rate. Okay, so it doesn't mean that the concentrations themselves have equaled out. It just means in terms of the reaction, in terms of the exchange that's happening, the forward rate and the reverse rate have equaled out to each other. Okay, I want that to be very, very clear. Now, this is actually where we're going to end this portion, because the next video we're going to do is actually a pretty short one. It's going to go through electrolysis. But yes, please write down any questions you have. We're going to do some practice with these so you get used to it, and so you can sort of understand what's happening with each phase of our electronic, our galvanic cell. All right, well, that's where we'll end this one. I'll see you all in class. Have a great day.